where it all started. So I'm really proud to announce our first keynote today. If y'all could give a big round of applause to Justin Reock from Gradle with a history of DevOps.
Thanks, Mikhail. Thanks, everybody, for being here. So this talk is going to be a little different than maybe some of the other ones you've seen. We're going to go back into ancient history, and we're going to look at the history of openness and where that's brought us kind of today. So I'm Justin Reock, Field CTO, Chief Evangelist at Gradle. My background is in software development. I spent a good 15 years of my career writing code and then moved into sort of more enterprise architecture. At some point, I ended up doing more PowerPoint than code, and that's kind of what took me here. Very proud to run the advocacy team at Gradle and have a few of our team members here today, too, that you can come and speak to. So I think pretty much probably everybody in this room is familiar with this quote. Right? This has sort of become, I think, the rallying cry for DevOps. But it's as true today as it was, maybe 10 years ago when this started to emerge. It's no longer the big beating the small, but the fast beating the slow. All right. It's no longer the big monolithic organizations that control everything, that just go and suck up all the business in the world. Now, it's the companies that can react quickly to the needs of the market and the feedback that they get from their customers, so that we can introduce these features sort of immediately and generate throughput for our business. But where did this mentality come from? Well, I like to tap on what I call the ancient business wisdom of the 70s and 80s when we talk about this kind of stuff. And I think some of you are probably going to be familiar with a couple of the concepts that we're going to go through, but let's really tear them apart and let's really think about how this relates to the state of modern DevOps. Anybody familiar with the goal? Who's read The Goal? Ellie Goldratt equations? All right. Ellie Goldratt was an interesting guy. He's a physicist, not a business person. He studied complex machinery. And he had sort of this spark of insight where he figured out, I can apply what I know about complex physics and mechanics to a business, because a business is a complex machine. And the nice thing about doing this type of comparison is that you can't break the laws of physics. So we can make really nice predictions about a way that an organization is probably going to perform. So his most famous work is called The Theory of Constraints. Some of you might have heard of this one as well. I guarantee you've heard of some of the concepts that come out of the theory of constraints. So things like value stream mapping, friction, bottlenecks, right? These were terms that weren't really introduced to business before the theory of constraints was publicized. And nowadays, still, the goal is taught in many MBA programs. And I really do think it's still probably the finest piece of business literature that was ever written. Part of it is because it's really not a business textbook. It's a fiction. It's a page-turning business drama about a manufacturing company struggling to sort of keep pace with their competitors. And a change agent comes in and introduces the theory of constraints and sort of fix the business. Sorry for the spoiler there. But I really do recommend reading this book, because DevOps, Agile, Lean, all of these newer practices that we like to talk about and perform, they all stem from this theory, the theory of constraints. So it again focuses on treating organizations like complex machines. Now, if you're not familiar with the goal, you might be familiar with this book. Anybody? Phoenix Project? All right. A few more of you. Yeah. So this modernizes the theory of constraints for software organizations. Okay? It takes everything that we learned about the manufacturing application of the theory of constraints and applies it to a software organization. But it's the same book. You open up the first page, you look at the blurb, they're like, hey, we just totally stole the goal and made it for software corporations. So they're very clear about this. But also a fun read. You kind of put yourself in the shoes of a VP of engineering struggling to get his software organization up to par. A change agent comes in and introduces DevOps, right? And the business thrives as a result. And this demonstrates the sort of relationship between DevOps and what we would call throughput optimization, right? Which is the right way that we should be thinking about highly productive organizations. So what does that mean? Well, the big breakthrough here was that previous to constraints-based thinking, this was sort of the way that we were prioritizing the values and bits of inventory that put together a business. So the theory of constraints sort of breaks down all complex machines into these three fundamental parts, right? So a machine has inventory that it uses some sort of cost to create throughput, okay? This could be any machine. A car takes gas so that the rubber meets the road and the car moves forward, right? The throughput of the car is its ability to move. But what about a business, all right? Well, when the theory of constraints was first introduced, most businesses were manufacturing organizations. So that meant that you took raw materials, that was your inventory, and through some cost, whether it was an energy cost of a machine or the human cost of a person that was assembling these raw materials into something that could sell, the business would create throughput. What's throughput for a business? Money, right? That's the engine that fuels a business. So when we think about throughput, we think about money generated by that business, okay? So the theory of constraints teaches us that this is the wrong method of prioritization. The only thing that really matters for a machine to be highly effective is throughput, right? Whatever that machine is producing. What that means is that we have to think less about cost and we have to think more about throughput. We're witnessing things happening in our software vertical right now which fly in the face of this basic theory. We're seeing tech layoffs all over the place, right? But the problem with a layoff is that it only controls cost. If you don't have some sort of plan to either maintain or even better improve the throughput of your business, then that layoff is going to be just a small Band-Aid. But overall, the health of your business will not improve, right? So the other part of this too is that inventory tends to rot, right? Inventory doesn't really sit still because we have this thing called the second law of thermodynamics, which is entropy, which tells us that nothing stands still. It's constantly disintegrating, right? And this is just as true for the physical raw materials that were part of a manufacturing organization back in the 70s and 80s as it is now for our code, right? These month-long release cycles that we used to have, what would happen to our code in the middle of that month? New security vulnerabilities might be announced, new dependencies, right? Things that require additional cost just to maintain the inventory. And if that inventory is spinning up cost and we're not converting it to code that we can charge money for, then we're not creating throughput. Now, a lot of us probably know this, but maybe haven't really broken it down to this angle because nowadays, this is sort of the way that we think about DevOps. So if you take these basic fundamental sort of parts and you apply this to a software organization, which is pretty much every organization now, well, cost is still cost. Still the organizational cost of paying your developers to do the work, writing code. Inventory is code in this case, and throughput is, of course, money. So why was it so important for us to release things like we were just talking about a second ago, where Shift is saying that we're able to push code 13 times a day? Well, it's because the sooner that you can get that code out into production making money for you, the less you have to worry about inventory rot, and the less, the more efficient the cost of your organization becomes. So really the conclusion here is that the only initiatives that are actually going to positively impact performance are the ones which increase throughput while simultaneously decreasing cost, right? This is the magic formula right here. This is why practices like just-in-time manufacturing, change management, ultimately agile, lean, and DevOps, they're the reason that these practices have sort of permeated and stayed alive is because they always do this. They do this in every case when they're practiced properly, right? So the good thing is if you have a new idea for your business, something that you think you could change or improve, put it past this statement right here. Is it going to do both of these things? Is it going to decrease your cost and increase your throughput? If it's not, don't do it. It's a waste of time. So what has this turned into? Well, we know this, right? The constant feedback loop of DevOps. Always move forward, always be releasing. Even if you release a bug, don't roll it back. Don't pull the conveyor belt back. Just release a fix like 2 seconds later because you built the right type of automation and deployment infrastructure to do that. This is probably a more concrete version of this, certainly not the only version, but just to give you an idea of some of the vendors who are involved and some of the different companies who are acting on different parts of this whole DevOps loop. You know, we've got folks helping us code with these Atlassian tech and of course Git. We got build systems like SBT and Maven and Gradle. I should probably mention that one too. Testing frameworks like Selenium and JUnit. Release platforms like Jenkins. But all of these are meant to work together to keep the conveyor belt moving forward, to keep the code inventory being converted into throughput for the business as fast as possible. All right, so there are many different technical actions that lead you to becoming a DevOps mature organization. There's not just one thing, right? Lots of different decisions that you have to make for the business, lots of different actions that you have to take. And these are just a few of these. So really, I think number one, choosing supported free software and an open first policy without any sort of deployment or accessibility constraints. Why? Because this allows your developers to start moving forward immediately with high quality software. It increases their throughput. Deploying cloud or container substrates with choreography, right? We know this too. You know, why? Again, so that someone else can handle the concern of how our deployed production software will be generating throughput for the business. It reduces the amount of friction between customers taking your software and paying you money for it. Deciding on viable and relevant API management solutions, all right? And basically, most software these days is just an interconnection of APIs, whether that's local programmatic APIs or REST APIs or gRPC APIs. But this is a time where we have to think about how we manage and control these things. And then building a fail-fast culture. Who's afraid to fail? Excellent. You shouldn't be. So, speaking of free software, there's a lot of problems with traditional closed development, right? And I think for the most part, the industry has actually moved past this, right? But let's think about what some of these things are. First of all, difficulty or slowness in obtaining software or media. I mean, I come from a time when literally, if you wanted to deploy some new Java application, you got to work with some provisioning team who's going to spin up some Windows server, and that's going to take like 2 weeks. And then once that server's spun up, well, maybe you need like a database on it, so that's going to take a couple more weeks for some procurement team to come in, get you the right license, set this thing up. So like maybe if you're lucky, a month after you want to do your work, you finally have the infrastructure upon which you can do it. Versus something like, I'm downloading CentOS and throwing Postgres on there, maybe in a Docker image, I'm done, I'm ready to go, right? Better way of doing things. Inflexibility in growth and scaling, all right? Even with taking something closed, as my business grows and I want to use more software, that makes my infrastructure more expensive, right? No ability to modify feature sets. I mean, maybe if you're lucky, the vendor will listen to your feedback, but let's be honest, that doesn't usually happen. You can't learn from and improve others' work. There's been a sort of paradox where some larger companies will say, I don't want my employees contributing to an open source project because what if one of my competitors is using the same open source project? I don't want to use my cost to improve the landscape for my competitors, right? And this argument is out there, but I just think it's wrong because the process of going through contribution and actually issuing a pull request and getting your pull request accepted and getting to know the members of that software community, the education that you bring to your business totally outvalues any possibility of losing your competitive edge. And less oversight by additional parties leads to less security on the whole. Another sort of controversial topic, but this seems to bear out. Linus Torvalds' many eyes theory seems to be working, right? Yes, it's easier to discover a vulnerability in open source, but yes, it's also easier to remediate it. People are doing crazy stuff with this right now. Who's familiar with Modern and the Open Rewrite project? Anybody looked at this? This is the future of vulnerability remediation and mitigation. Not only is this platform able to detect software patterns that are probably exploitable, but it also has recipes to auto-correct them at scale, right? And we can do that. We can issue pull requests against 30,000 open source projects that have this one vulnerability because we have this open development pattern. But it wasn't always like this. I think of this as sort of the the alchemist's dilemma, right? Sort of early closed development. So alchemists, I mean, they get kind of a bad rep, considered sort of superstitious and pseudoscience, and I think that's fair. But they were operating pretty early for their time, but they were doing things in secret, right? They weren't sharing their knowledge with others. So a lot of them were doing things like drinking mercury and lead to try to live forever. And it would have been great if they could have shared with other alchemists, hey, you shouldn't drink lead. But they didn't, right? Everything was being done sort of in their own silo. And so we don't really know what to attribute in terms of modern science to this group of practitioners because they didn't tell anybody what they were doing. Now, there was a very specific version of this took place around 600 BC or so in the ancient city of Crotone, which is now southern Italy. Some of you may recognize this guy, Pythagoras. If you don't recognize him by face, you probably at least know the Pythagorean theorem, the equation that lets us calculate the hypotenuse distance of a right triangle, a squared plus b squared equals c squared. The interesting thing about Pythagoras, and where you have to put yourselves in terms of understanding what geometry meant to that ancient civilization, this was the esoteric knowledge that built infrastructure, right? If it wasn't for geometry, you wouldn't have plumbing, you wouldn't have buildings, you wouldn't have columns, right? You wouldn't have these things that built at the time, at 600 BC, what was considered modern infrastructure. So in some ways, this knowledge was considered divine, which I think in some ways are non-technical people who talk to us and we talk about code and they have no idea what we're talking about, right? But they understand that all the infrastructure around it is sort of built on this skill set, built on this knowledge, right? That is the landscape that we're living in right now. IDC predicted in October of 2020 that the world global GDP would be 65% digitized by 2022. That prediction came true. Now, IDC hasn't pushed their new study yet, but think about that. 65% of the global GDP held up by software, right? But that's really not that different than sacred geometry at the time. So Pythagoras made a big mistake. He created two different schools within his school of geometry in Crotone. And again, this was highly guarded knowledge that was very important. He created two schools of thought, the mathematicoi, or sort of the inner circle, and then the achismatics, the listeners, who were the outer circle of the school. Now, the mathematicoi were the only ones who were allowed to learn and practice geometry. And Pythagoras was sort of arbitrary about like who could be, in this part of the school, versus the achismatics who were basically just running chores for the school, not really learning anything, right? And then outside of the school, Pythagoras was also very selective about who would be allowed in. So along comes this nobleman, Cylon, not from Battlestar Galactica, although maybe named after that, I don't know. But he was a nobleman and leading citizen of the city of Crotone. And because of that birthright, he felt that he should be accepted into Pythagoras' inner circle. He considered it his birthright. Birthright is something that we have thankfully done away with, but used to be the guiding practice of hierarchy in our society. You were divinely gifted with some sort of nobility that made you part of the upper echelon of society and guaranteed certain privileges that weren't guaranteed to others. So Pythagoras repeatedly refused Cylon's request to be part of the school, which led to his exile. Cylon revolted against the Pythagorean school in 509 BC, and many of the students were killed in this revolt, and Pythagoras ended up dying in exile. And we also don't know what else to attribute to Pythagoras, because just like the alchemists, it wasn't clear who was actually doing what work, because nothing was being shared. So thankfully, we would sort of come out of this time of superstition and nobility and all these sort of constraints to our progress when we would come upon historically a time called the Age of Enlightenment, right? Where we sort of threw away some of these notions of nobility and secrecy and started to share knowledge. And I think the turning point is often described by this quote by Immanuel Kant: "Dare to know, have courage to use your own reason." Right? Just because the nobility says something is true, that doesn't make it true. right? Use your own critical thought. Be an individual. Bacon makes everything better. Sir Francis Bacon would sort of continue this thought process with the publication of the Novum Organum, which was the basis for a philosophy called reductionism, right? Reductionism says, instead of looking at the hermetic view of a thing, which was superstitious, weird stuff, let's boil it down to individual components of the problem, right? What individual parts, what quantum units are actually part of this problem? Let's pick those apart and let's deal with those. Now, this type of thinking, fundamentally different than what was happening before in terms of secret knowledge, nobility, guarded secrets, these sort of things. This would explode us into a whole new cultural way of handling knowledge. Some principles of enlightenment should seem pretty familiar to us for those who have been operating with free software and using things that are within the public domain. Because the sharing of ideas through publication is one of the first guiding principles of enlightenment. This would lead to the rise of the public sphere, the public domain, the idea that the knowledge that we've gleaned from the universe belongs to all of us, right? And not just a select few. Individual liberty and creative freedom would be values that were espoused from this point of time. This would lead us to things like scientific method and reductionism. Some of you may be familiar with Sir Isaac Newton. He did something that was completely different than when you look at, for instance, the philosophies of somebody like Pythagoras. He published this book, Principia Mathematica. He said, I've learned all these things about math, and now I want to share that with other mathematicians and engineers, right? I want to teach what I've learned to them to try to lift all of us up, to try to allow us to break forward with progress, right? This was radical at the time. The rise of the Florentine bodega would come out of this. These are open community sculptors, artists, poets, philosophers, all meeting in the same place and exchanging ideas. Leonardo da Vinci was discovered in a Florentine bodega, right? This is so different than what you had in terms of guarded knowledge. These are finally great minds working together, sharing ideas for the purpose of progress. The Parisian salon, another interesting sort of phenomenon but very similar, right? The thinkers of the time would gather together and exchange ideas. Parisian salon reminds me a little bit of GitHub, if you'll allow me that stretch. It's the ability for like-minded people to work together towards a common goal. So this is what things look like now as a result of all this freedom and openness. We now have a, say, fairly fragmented landscape, but we have all these different solutions that are available to us, many of which are free, that can help us achieve better throughput for our business, can help us achieve better productivity. But the choices can be a little scary. Luckily, the CNCF has put together what I think is this really great trail map. Anybody seen this before? This is really cool. This is sort of boiled down, hey, if you want to go from zero to cloud, these are the baked, incubated CNCF projects that we recommend for you to get there, okay? But this has actually changed the way that we have to write code. All of this cool cloud native, heavy throughput stuff doesn't work for our old monolithic ways of thinking about code. It's forced us to write code in a different way. So again, not to age myself too much, but I did come from a time when deploying a new application meant racking some $10,000 Dell server that you're going to set up in some database somewhere. You're going to run one application on it because you have to run your applications in isolation, right? So you'd be utilizing 1, maybe 2% of this server, right? But at least, your business application was up. And at the end of the day, this was true back then, it's true now. Anybody only cares about the app, right? We as a group can talk about Kubernetes and service mesh and all these things that we love to talk about in terms of deployment. Guess who cares about that at the business level? Nobody. They just want the app to be up. And so this was how we achieved it back then. The app would stay up, but it was expensive and wasteful, right? So along came virtualization, great, okay, we had that little mid-step. We could take this physical server, slice it up into a bunch of virtual servers, and then host applications in those virtual servers. I don't mean to trivialize it, because this was highly revolutionary at the time. Ensured much more efficient utilization of a single physical machine, and ensured that applications are, continue to be isolated from one another, so that they're not starving resources and all these things. But is this efficient as it could be? Well, no. If you take a look at this picture, we have a better solution where a hypervisor application is able to slice up our physical resources into multiple virtual machines, but we still have to install a separate operating system on all of these. So we did better. We came along with containers. So rather than having that whole virtual machine, a single container, which is really just a stripped down file system hack, contains all the important parts of the operating system and everything the app needs to be able to live. But it runs on top of a container engine instead of an entire emulated piece of hardware. So containers are then isolated, and they're powered by one underlying OS, right, on the physical machine, not individual OSs on virtual machines. Great. So now we've got a single physical machine, single operating system, and then any number of applications running in their own isolated container environments. Right? So this is a better picture. But what this has done is created the need for a whole new ecosystem of software. So now that we have all these great things that we can chunk up into containers, well, you can't just do that and expect things to be better. Right now you have to have a whole framework around these little stripped down fast containers that provides automation, orchestration, all of these things so that they can work together. You have to have access to network and storage resources, something to manage container lifecycle. You need firewalling and routing and orchestration and basically everything else that goes into building a data center, right? I mean, what is a container engine like Kubernetes if it's not a virtual data center in a box, right? And so, this seems to be sort of the prevailing ecosystem right now. I don't think I need to spend too much time talking about Kubernetes. I think plenty of people will be doing that today and tomorrow. But I think the important part of this is to understand that it is an ecosystem. Right? It's not one single solution. And with this ecosystem, you can, of course, deploy, scale, roll out new features, and optimize what you want to do. We get back to the original slide. Applications like Kubernetes and frameworks like that allow us to convert our inventory and cost into throughput for the business much faster, right? And that's why it's been so successful. That's why it's eaten the landscape. But this ecosystem has definitely changed the way that we write software, right? The way that we actually approach our craft. Anybody heard of the 12-factor application before? All right, yeah, good number of you. If you haven't, 12-factor is really nice. It's a rubric for saying how much friction should I expect to deal with when I launch my application into a cloud-like environment, all right? Now, this isn't to say that if you're not following all 12 factors of development that your cloud migration is going to fail. It's not true. But there's an inverse relationship between the 12-factor maturity of your application and the friction that you'll experience deploying that application into cloud, right? The less 12-factor your app, the harder it's going to be to maintain in a cloud-like environment. So we have to rethink now the way that we write our software so that it can live in ephemeral, non-permanent environments that might spin up for 2 seconds, process some data, and then disappear forever. And that just is so much different than the way that we've thought about code in the past. So the 12 factors are broken down into 12 factors. And we won't go through necessarily each of these, but if you look at them together, all of these things are specifically dealing with things that cause frustration and toil when moving code into a cloud-like environment. We should have our code base in a single repository so that we're not deploying from multiple places. We should be explicitly declaring and isolating our dependencies, not including them in our artifacts. We should be storing our configuration in the environment itself, not forcing our application to reach outside its environment, which it might not know how to do to grab its basic configuration, right? Dev prod parity, factor number 10. This is something that was directly dealt with by Docker, right? How do we ensure that the environment that I'm working in and developing now matches the environment where my code will ultimately be running? This was a real problem back in the late 90s and early aughts. the whole adage, well, it worked on my laptop, that was way worse back then, right? Because we were talking about like production class applications and QA teams that would, create additional friction and time between getting our code, which is rotting, out to production, creating throughput, right? So if you look at the 12 factors, these can be really useful for understanding how your cloud migration is going to go, right? Grade yourself by this and be honest about it, right? Are you treating logs as event streams, or are you forcing some build engineer or DevOps team to like scrape the console log output of some Kubernetes pod that destroyed itself like a day before to try to solve a problem, right? Are your admin processes requiring you to like SSH into these arbitrary containers and run commands to keep your application up and going? If any of those things are true, then you have some improvements to make, right? But the good news is the 12 factors can kind of keep you on rails with that. So that's kind of the state of the modern landscape. I think we've adopted open source technology. We realize that openness is better for us than the way that things have been done in the past. I think we understand that having easy and accessible access to high quality software improves the throughput of our business and makes us do things better. But are we done? No, we're never done. We're always looking for new ways that we can decrease that time window between the cost of creating the code and generating money for the business. So we have to start asking ourselves questions like, what comes after DevOps, right? What's next? Now that we've sort of commoditized this part of the landscape, now that we've improved the way that we deploy and monitor, what should we chase after? Well, I think it's this. I think that a lot of the bottlenecks that have been solved in the idea of deployment and operations have just created a new set of primary bottlenecks, thinking in terms of a value stream and thinking in terms of constraints. And those bottlenecks have just gotten further and further left, right? Now that we've sort of commoditized the way that we deploy software, well, what's going on with the way that we write software, right? Developers are still dealing with pain and toil and friction that is decreasing our ability to immediately create throughput from our work. So don't put yourself in the shoes of these kids for a minute, right? What are they doing? Well, they're joyful, right? Why are they joyful? Well, they're learning how to code, right? It's an ecstatic feeling. Those of us who have written code, we know that this is a highly creative and also scientific process, right? It's this wonderful soup of left brain and right brain activity. On the one hand, we're visualizing a problem and we're thinking about a solution to that problem. So it's very creative. But then we do something scientific. We create a hypothesis with a build toolchain. We say, hey, I think this code I just wrote is going to solve this problem. So I'm going to compile it, build it, run my tests, and find out whether I'm right? Getting my feedback from the build toolchain, the feedback cycle, right? The feedback cycle. Write code, run it, see if it worked over and over and over and over again. The basic unit of developer experience. So these kids, maybe they just ran system.out.println hello world, and they go and it showed up on the screen. Oh, wow, look at what we did. That's amazing. Or if you're a Kotlin fan, they just did println hello world. But either way, fast, great feedback, joyous. We are ecstatic. Our left brain, right brain, dopamine firing. We're in good shape. So I want you to imagine that these kids are actually dealing with what is a more realistic software landscape, not a hello world application, that these kids are waiting 30 seconds, a minute, 10 minutes, an hour, 20 hours, in some of the more extreme cases that we've seen, to get that feedback on the screen, to get that hello world. They're gonna look like this, they're gonna look like this. And they're gonna go find some other hobby. So this is where I like to ask a very simple question. The length of that feedback unit, the distance between the work and the dopamine hit that keeps you going. Who's tracking this? Anybody keeping track of how long developers are waiting on their laptops for builds to complete? No, one person, yeah, one person. Oh, two, oh, a few people, yeah, good. That's the response I always get. None of us are doing this, right? But why? This is the most fundamental unit of developer experience, and we're just completely ignoring it. And what is the 3,000-year-old adage that was as true back then as it is now? What gets measured gets improved. So if you take one thing from this talk, one thing, go back and figure out a way to track this piece of data right here. It's easy to do. Just look at your build system. Most of them are open source. Create a small plugin to just get that little piece of data. How long did this take? Stick it to some Prometheus database, throw a Grafana dashboard in front of it. I guarantee you, if you do this one thing, you're not going to be able to unsee this problem. And that's going to lead you to the next phase of developer productivity engineering, which is what we're talking about right now, DPE, the next thing after DevOps. Now, this isn't to suggest, that there's some pie in the sky reason for this being the next big thing in software development. It's actually very literal, right? What is the next set of primary bottlenecks that we have to deal with? Those bottlenecks right there in the developer experience. Long cycle times, long testing times, flaky tests, avoidable failures, toil, friction, and frustration. Our developers are still dealing with this. Netflix was one of the first, I would say, pioneering companies of this discipline, developer productivity engineering. They took their platform engineering teams and converted some of them into developer productivity engineers. And they focused only on improving throughput for the tool chain. So when I say that this is the next big thing, it's, again, very literal. Who's going to deal with the next set of bottlenecks? So Danny Thomas is a developer productivity engineer at Netflix. I was interviewing him a couple of years ago. We were talking about productivity. He said something that is now indelibly etched in my brain. I can't forget it. He said it is staggering the amount of toil and friction and frustration that engineers are willing to put up with. As a franchise, we don't complain about this stuff. A lot of us just sort of think it's an occupational hazard of being a developer. Oh yeah, that sucks. I got to wait an hour for my build to complete. That's just life. Oh, my tests are flaky. Probably going to spend my afternoon trying to debug one of those with not enough data and relying on CI and people outside of me to help me with this. So we got to get past this. We need to introduce developer productivity engineering at large. Now, what is it? For all that theory, it just takes an engineering approach to productivity, right? We look at the software tool chain. We apply telemetry and acceleration features and analytics to find out, is the build as fast as it could possibly be? Which is the right mindset, but it's not the mindset that we're in. We always ask ourselves a different question. Is it fast enough? Are the developers okay? It's the wrong question. The right question, what we owe this workforce that is holding up 65% of the global GDP is the build as fast as it can possibly be, given all acceleration and analytic technologies? That is what we owe this workforce. And we can do it. We have tooling that can let us do this. And it's not hard to sell to your boss. All of this stuff, because it decreases cost and increases throughput, aligns with strategic management goals: faster time to market, reduce costs, and improve quality of our product. So to be really clear, what does DPE solve? Well, if you can imagine that this is a developer and that these things surrounding the developer are cycle times, feedback cycles. And it used to be a local environment, but this could also be remote or work that's being done in CI. Sometimes things are fine. Sometimes things take too long. We talked about that a little bit. The cycle time is too long. The test cycle is too long. The build cycle is too long. Sometimes it takes too long to fix. Right? Just because a build goes red, that doesn't mean that you're out of your flow state, right? It's a new problem to solve. Great, we love solving problems. That's why we're here, right? But if 45 minutes later, you're still slogging through some system to try to get the data that you need to figure out what actually went wrong, that is not creative flow. That is toil and friction and frustration. And then finally, the worst one, the broken feedback cycle that could have been avoided altogether if we'd applied just the slightest amount of analytics or observation. Detect flaky tests, put them on a dashboard, do something about them, aggregate failures, figure out which part of the build is failing more often. If you have 1 hour to improve your build tool chain, where should you spend your time? Right now, that's a hard question to answer because we're not capturing data in general. So instead, we're relying on anecdotal things. Oh, this developer said this part of the build system really sucks, so I should probably do something about that. But what if that developer is just being like all of us and is just subjective. Like they think it's a big problem, but it's not actually impacting anybody else. You don't know unless you're capturing this data. So DPE organizations do that. I'm not going to get mired down on this slide. I just want to say that DPE sort of addresses these, I would say, 5 pain points. So wait times, context switching, inefficient failure troubleshooting, flaky tests, and other types of avoidable failures. No metrics or KPI observability over the developer experience, and inefficient use of CI. Right? If we eliminate flaky tests from the tool chain, what do we do with flaky tests now? Let's be honest. Run it again, run it again, run it again, run it again. Oh, it passed, good, except the PR. That's it, right? We need to be observing these things and doing things about them proactively. Okay, so I think we're kind of up on time here. Yes, we are. If you'd like to learn more about DPE, we put together a really nice learning center with videos, white papers, blogs, all these kinds of things. You can read the blog from Danny Thomas where he talked about toil and friction and frustration. Excellent blog article. This will get you started down your path, right? How can I maybe turn our platform teams into productivity teams? This is the microeconomics. If you look at the Ubers, the Squares, the LinkedIns, the Spotifys, the Twitters, the Netflixes, they've gone through this interesting evolution where DevOps and SRE type people became platform engineers. But then those platform engineers turned into productivity engineers, right? The macroeconomics of this are starting to bear out. And you can do this for your organization. What if you were the person who 10 years ago introduced DevOps principles to your company? What does that do for your career, right? Well, the good news is this has not been commoditized at all. This is still pretty new, right? Netflix only put this together 7 years ago, right? And the industry is still catching up. So you can be a hero for your organization. We also have a book on this, 81 pages in its second revision. You'll see Gradle here on the front cover. You won't see Gradle mentioned anywhere else in the book. It is highly vendor agnostic, as this practice is, language and platform agnostic as well. But you'll be able to explore use cases, data, go deeper into this practice than we went today. And that's really it. If you have any questions, please reach out. I'll be here for most of the day, as well as several of my colleagues from Gradle. And thank you, DevOps Days, for giving us this platform to speak. And I hope you really enjoy the rest of the show.
Thank you. Thank you, Justin. Welcome back.